Hi everyone, my name is Jae-Young Lee, and I'm from University of Illinois at Urbana-Champaign. I'll present our work, PatchMatch-based neighborhood consensus for semantic correspondence. We're interested in establishing correspondence across two images that have objects of the same category. This task is challenging because there are large intra-class appearance variations and because semantic correspondences are sometimes ambiguous. Rocco et al. Proposed Neighborhood Consensus Network, NCNet, that addresses these challenges. The main idea of NCNet is to train a network that uses a series of 4D convolutions to improve the dense 4D correlation map. The 4D correlation map measures the dense similarity between the source and the target images and is created by a dense dot product between all permutations of source feature vectors to target feature vectors. The 4D convolution in NCNet runs on top of the 4D correlation, which convolves over all indices with the learnable 4D kernel to refine the 4D correlation map. The correspondence is estimated by taking the argmax over the refined correlation map. We propose PMNC, PatchMatch-based neighborhood consensus for semantic correspondence. The core idea of PMNC is to reduce the number of computations in the correlation map refinement through the PatchMatch updates. We first compute the 4D correlation map, then obtain dense correspondence through the raw correlation map, and finally refine the dense correspondence through the number of PatchMatch iterations. The core of PMNC is the PatchMatch-based refinement of the dense correspondence map. Given source to target key points, we define propagation candidates as the correspondence values of the direct neighbors. Then, we use the neighborhood consensus-based scoring function to evaluate a 4D patch centered at the source point and the candidate target points of the 4D correlation map. Once we evaluate all the candidates, we find the candidate with the maximum score and replace the correspondence with the best candidate. The problem with the PatchMatch update is that it is not end-to-end differentiable due to the hard argmax-based selection. So, we propose a proxy architecture to train the patch scoring function. We use ground truth annotation pairs to supervise our model training. Given a dense 4D correlation map, we use source annotations to generate a probability distribution of the matching target annotation through the patch scoring function. In detail, for each ground truth source annotation located at ij, we compute 4D patch scores centered at ij of the source feature map to all the pixels in the target feature map. Normalizing the 2D score map with the softmax gives us a probability distribution of the target key points according to the scoring function. Then, we compute the ground truth target annotation distribution as a Gaussian distribution centered at the ground truth target annotation. Finally, we compute the cross entropy between the expected and the ground truth distribution. We evaluate our work using the PCK metric, which is the percent of inlier matches given a radius of inliers controlled by a hyperparameter alpha. This is an example case from the PF Pascal dataset. The orange dots on the leftmost image represents source key points. The green dots and the circles on the right three images represent the ground truth target key points and their inlier radii. The orange dots on the right three images represent the estimated key point locations for each method. Compared to the baselines, PMNC more accurately localizes the matching key points. Compared to the baselines, our method is faster, uses less memory, and localizes key points more accurately over all alpha thresholds. We also show that increasing the spatial resolution allows higher accuracy at the cost of longer processing time and larger memory usage. These are examples from the more challenging SPARE71K dataset that contain larger viewpoint and scale variations. We show that our method works robustly under these challenging cases. Moreover, we analyze the evaluation per nuisance and show that our method performs better than the baseline method by a significant margin. Thank you for listening. Our code is available at the link shown below. Please visit our website.